In this video, we'll derive the formula for accumulated value. So watch this video only if you want the proof of where this formula comes from. Basically, the crux behind this weird looking formula. So yeah, if you're still watching this, the terminologies involved in this formula are these. C is my annual installment or the installment that I make at the end of each year. N is the number of years, that is the time period for which I am making the installments. And R is the rate of interest, it's a fixed rate of interest, and I'll denote it as a percentage per annum. So let's say if my rate of interest were 10% per annum, so in that case R would be just 10. And I have this small I as R by 100. So every time I don't have to mention 10%, I can just write it 10. So I will be just 10 by 100, which is just 0.1. That's one just piece of notation. So the basic formula that of the accumulated value. So this is nothing but the future value of all the installments that I'm going to make, and this accumulated value A is given by my annual installment C divided by this I into this weird looking expression. It is a 1 plus I raised to n minus 1. And then we have a bunch of other formulas. We'll derive them in future videos, but this video is all about deriving this formula. And to derive that, we require the knowledge of geometric progressions, and basically the sum of the n terms of a geometric progression. So I assume you are familiar with geometric progressions, wherein we have a first term A and a common ratio R. So if we were to find the sum of the first n terms, the n terms would look something like this. The first term is A, the next term is A into R, the next term is A into R squared, and so on. The nth term will be A into R raised to n minus 1. Remember, n minus 1 because we are starting with R raised to 0. So A is just A into R raised to 0. So that's why the nth term is A into R raised to n minus 1. So from the theory of geometric progressions, we know that this sum can be written as these two formulas. This is A times R raised to n minus 1 divided by R minus 1, and it can also be written as A times 1 minus R raised to n divided by 1 minus R. And I know some people say that you should use one formula when you have R greater than 1 and the other formula when you have R less than 1. But I say it makes no difference, because if you look carefully, the only difference between these two expressions is that the numerator is multiplied by minus 1 and the denominator is multiplied by minus 1. So when you multiply the numerator and denominator by minus 1, it's as good as multiplying just by 1. So these actually are the same formula. They are just two ways of writing the same formula, and both will use one of them when in this while deriving the formula for accumulated value, the future value of my installments. Basically, the accumulated value under immediate annuity. This is the concept of immediate annuity. So the premise is that I make an installment of C at the end of each year for n years, and I get a rate of interest R. This is compounded annually. This is as a rate of interest compounded annually. So I want to see what my accumulated value will look like at the end of these n years. So this is the formula, and you can come up to this formula by looking at the future value of each and every installment that you make. So if I were to derive the formula, I would start with A. Let's think about the first installment that I make. I make the installment C, which will gain compound interest, but it will gain compound interest for n minus 1 years, because I am investing it at the end of the first year. So the from the formula for compound interest, this will gain compound interest for n minus 1 years. So I'll multiply it with a factor which is being raised to n minus 1, and that factor is nothing but 1 plus R by 100, right? This is just theory of compound interest. And we have a notation for R by 100. R by 100 is nothing but I. So I can really replace this with just an I. So this is nothing but if I were to write this properly, it would be C into 1 plus I raised to n minus 1. Remember n minus 1 because my first installment will get interest will be calculated on that for n minus 1 years. Now for the next installment, I'll have the same installment again, but this is at the end of the second year. So interest will be calculated on this for the remaining n minus 2 years. So I'll have the same expression raised to the n minus 2 power, and so on and so on up to the second last installment that I make. Again, it's the same installment, and it will gain interest for 1 year. So it is as good as multiplying by just 1 plus I raised to just 1. And the last installment, it won't gain any interest because it is at the end of my annuity. So it is just that value C. So yeah, at the get-go, it might not seem very clear, but if I write it in a succinct manner, that is like this. If I write the last term first, then the previous term is C into 1 plus I. Then I hope you realize that the previous term will be C into 1 plus I squared, because that term will gain interest for 2 years. So it will have a factor of 1 plus I squared. And so on up to the first term will become the last term here, so it will be just a C into 1 plus I raised to n minus 1. And what we have here is nothing but a geometric sequence. So the geometric sequence with first term C and a common ratio of 1 plus I. And we have n terms for those. Again, remember, because the last term involves n minus 1, and because we are starting with a 0 power, there are n terms involved. And using the formula for the geometric progression, this sum is nothing but my first term C. Now I am using this formula. Here my R is 1 plus I, because 1 plus I is the factor that is being multiplied each time to get the new term. So R is 1 plus I. According to the formula, I need to raise it to the nth power. Then I need to subtract 1. This is my numerator. And my denominator is R, which is my 1 plus I minus 1, and 1 plus I minus 1 is just I, right? So my denominator is just I, which I can write it along with C. So it is nothing but C divided by I into whatever my expression here is, 1 plus I raised to n minus 1. And if you see clearly that this is actually what we expected to get from the formula here is C by I, 1 plus I raised to n minus 1. And yeah, this ends the proof. We started with each installment, we calculated the interest gained on that for various periods, and then we summed it to get the future value of all my installments to give you this. So yeah, this actually makes sense. This formula, again, it's not God given. There's a logical proof for that, and the major crux for this derivation is the formula for geometric progression, the sum of the first n terms of geometric progression. So once you have the setup of each and every installment that you are making, and for how much period interest is being calculated, you have the sequence, and just by using the formula for the sum of the sequence, you get this formula. We'll derive the next formula in the next video.